So this box is at rest on a 50-degree ramp, and we're asked, there's an applied force helping it to stay at rest, and we're asked to figure out what that applied force needs to be. So let's just think what would happen if there was no applied force. Well, the only thing that could happen would be the box might slide down the ramp. If the gravity overcomes static friction, then it would slide down the ramp. So this question only makes sense if the applied force is trying to help keep the box up, help prevent it from sliding down. Okay, so in some questions you have to think about which way the applied force is actually pointing. In some cases that's actually uncertain. You have to actually do some analysis before you're certain about which way the applied force is. But in this situation, it's pretty clear that it has to be pushing the box up because it's trying to keep it at rest. And the only thing that could happen is it slides down. So that's why it's got to be pointing up. All right, I'm rambling a bit here. Let's get solving. I'm going to define my positive directions. I'll choose down the ramp as my positive x direction. And the direction of the normal force is my positive y direction, my perpendicular reference directions. Okay, I'll go with the free body diagram. And I'll start with gravity, which goes straight down. And I will draw in the perpendicular components. FGY, FGX. I'll have a normal force. And it's going to be equal in magnitude to FGY. The forces are balanced in the direction that's perpendicular to the ramp. And there's going to be friction. Now, I'm assuming that the friction is going to be smaller than FGX because the question's kind of implying we actually need some more force to help it be balanced. We need some more applied force to help it be balanced. So I'll assume friction's smaller than FGX, and I'll draw in an applied force to try to make up for that, to balance out the x component of gravity. Okay, so I have that the normal force is equal in magnitude to FGY. I'm just going to go ahead and replace FGY with mg cosine theta. So that's just the y component of gravity. And then in the x direction, okay, we're getting a bit more complicated here. We've got 3 vectors involved, and, well, they're going to be balanced because this is staying at rest. So I'll go with magnitudes here. I'll say that the magnitude of the applied force plus the magnitude of the force of friction has to equal to the x component of gravity. It's got to balance out the x component of gravity. So the applied force and the force of friction, those are both pointing in the same direction. They're pointing up the ramp. And the x component of gravity is pointing down the ramp. So that's why I put them on the sides that I put them in. Okay, this needs to be isolated for the applied force. That's what we're solving for. So I'll simply subtract the force of friction from both sides. And then I'll do some equation stuff. So the x component of gravity has the equation mg sine theta. And the force of friction has the equation mu times normal force I'm going to number my equations here, 1 and 2. And what's going to happen is this expression for normal force, mg cos theta, I'm going to substitute that into equation 2 for where there's normal force. Sub 1 into 2. So I'll go ahead and do that. Mg sine theta stays the same, minus mu. So now I'm changing this to mg cosine of theta. And at this point, I'm good to substitute in all the values if I wish. I have them all. Okay, I have the mass, I know g, I have the angle, and I have the coefficient of friction. Yeah, I have all of it. I will actually common factor first mg so that I can type a little less in my calculator. That's just common factoring. So 40 times 9.8 for mg, and then sine of the angle 50 degrees minus mu 0.5 times cosine of the angle 50 degrees. All right, still typing in a lot in the calculator. Such is physics life, I guess. Okay, so I'm coming up with 174 newtons, a positive value, which I'm going to have to round to 2 sig figs because of all those numbers with 2 sig figs. So I'll say 1.7 times 10 squared newtons. I'll make a final statement here as a vector, so the applied force should point, no, that's wrong. The applied force should point up the ramp, but I defined the positive x as down the ramp, so this is actually negative. Negative 174 x hat. All right, that's the force needed to keep it at rest.